Hello, my name is Ashley Imhoff. I'm a Physics 1 student, and my long term I did is the influence of symmetry in facial attraction. So my question that triggered me to do this project was, what is it about someone's face that makes them an easy target to be positively, attractively looked at? I kept going back and forth between is it the features or the symmetry in your face. But a lot of people, or I would say all people, don't know the symmetry level in their face, so I thought it would be interesting to test to see if that correlates with your attraction level. With that being said, my claim was as symmetry in the face increases, the attraction for that particular face will increase as well. People will be visually drawn to a symmetric face rather than a non-symmetrical face. This is just due to alignment. I feel people enjoy looking at aligned things with equal measurements. So my symmetry setup, I chose 4 faces to test, shown right in the middle here. And then I measured the symmetry in each face using a variety of increments I will show you in the next 2 slides. And my materials I used to measure symmetry was pretty basic. I just used a ruler, a calculator, some colored pens, and the printed faces. So this was my attraction setup. Since there's not really a specific way to measure attraction, it's an opinion-based thing. It's different for everyone. So the best way to measure, I thought, was to create a poll that has participants choose which face they think looks best to them. And then these results will show me which face is most attractive. And so then the end goal of this whole project is to see if the most symmetric face that I will measure is also correlated to the most attractive face done in this survey. So this is the increments I used to measure the symmetry in each of the faces. So the first one I did was pretty basic. It's face length divided by width. That should equal 1.6 centimeters. That's just a handbook value I found on Google. That's represented by the black vertical line versus the black horizontal line down by the chin. We have the tri-length should equal 5 centimeters. Those are the red lines on the face, which is the top of the forehead to in between the eyebrows to the bottom of the nose to the bottom of the chin. Once you divvy those up, they should each equal 5 centimeters. And then we have equal eye width to in between width. That is represented by the purple line on the actual eye. On both right and left eyes to the yellow line in between, that is the width, they should equal the same. So basically you should be able to fit a third eye right in this space right here without any gapping or squishing. And then we have the facial triangles, which is the corner of the eye to the corner of the nose to the corner of the lip and then back up. I took the area of those for each side to see if they're the same on each side, just to measure that general area of the cheek portion of your face. And then we have the nose to forehead ratio. Those should both equal 5 centimeters each, represented by the light blue line. So these were our faces I chose to test. I have Dylan for person number 1, Olivia person 2, Ellie person 3, and Joshua person 4. Each person displays different features and coloration, which is why I picked them. So for each person, I made a data table showing their real measures in the middle column versus the given measures from the handbook measures. So the 1.65 centimeters and then the dimensions and then the differences on the right column. So we have 1.7 centimeters for his length divided by width minus the 1.6 to get 0.1. Then we have the 3 face portions, which is a 5.4 centimeters, which is from the forehead to the eyebrows to the nose to the chin. We get 5 centimeters for the handbook value. Subtract those to get 0.4 centimeter difference, width of eye to width in between. So the width of the eye was just 2.4 centimeters in comparison to a 2.6 width in between. Subtracted those to get 0.2 centimeters. Then we have the left facial triangle 3.5 centimeters squared in comparison to the 3.3 centimeters squared. Subtracted those to get the 0.2 centimeters squared. Nose to forehead ratio was 5 to 6 because the nose was perfect 5 centimeters and the forehead was 6 centimeters, so we have a 0 to 1 ratio. I added those all up together to get a total symmetric difference of 0.9. For Olivia, I did the same exact thing. We have 1.8 minus the 1.6 to get a 0.2 difference. 5.1 minus the 5 was just a small difference of 0.1. Then we have the 2.5 to 2.7. You can visibly see the width in between the eye is a little bit bigger than the actual eye, which is why we have a 0.2 difference. we have a 3.5 left triangle versus a 3.4 right triangle. That creates a tiny difference of 0.1. And then we have the nose to forehead ratio was 1:1. She was off by 1 centimeter for each increment for the nose and forehead. So that gives us a total symmetric difference of 0.6. So for Ellie, I did the same exact thing. She has 1.6 to 1.6. That's perfect. So we had a 0 centimeter difference, and then the 3 facial portions were a little high. 5.8 centimeters minus the 5 centimeters equals 0.8 centimeters. That is a larger difference than the other 2 had. And then we have the width of the eye to width in between. The width in between was 3.1 centimeters. You can visibly see that one again is larger than the 2.8 width of the eye. So that gave us a 0.3 centimeter difference. Left facial triangle was 5.9 centimeters squared in comparison to the right, which was only 5 centimeters squared. That is also a larger difference than the other 2 for the triangle. So that gave us a 0.9 centimeters squared difference. Nose to forehead. Nose was perfect 5 centimeters in comparison to a 6 centimeter forehead. So that gave us a 0:1 ratio. So this is the last face I tested. So the first increment, face length divided by width, he had a 1.7 and the real measure was 1.6. So we had a difference of 0.1 centimeters. He had an average of 5.3 centimeters for the 3 facial portions when the real handbook value was 5. So that gave us a 0.3 centimeter difference. 2.6 to the width in between the eyes to 2.4 centimeters of the actual eyes. That gives us a difference of 0.2 centimeters. Left facial triangle was 3.5 centimeters squared in comparison to the right triangle, which was 3 centimeters squared. That gave us a difference of 0.5 centimeters squared. The nose to forehead was 5 centimeters, which it should be, and the forehead was a little bigger with 6, so that gave us a ratio of 0:1. So that gave us a total symmetric difference of 1.1. After I calculated the differences for each of the faces, I was able to rank them from most symmetric to least symmetric. So most symmetric was Olivia with a 0.6 difference. Second symmetric was Dylan with a 0.9 symmetric difference. Third was Joshua with a 1.1 symmetric difference, and fourth was Ellie with a 2 symmetric difference. So the smaller the difference, the more symmetric the faces. As you can see, we have a 0.6 all the way up to a 2. So as we go up this line, the symmetry decreases, and the closer to 0, the more symmetry is displayed, as you can see. So this was the attraction survey I put out after I did the measurements. So I just created a poll that had the faces on it, and then the participants just choose which face they like the best. I had a mix of both boys and girls choosing, and I had about 35 responses. And the point of this was just to see if the mathematical results from the last slide matched up with this. So Olivia had 40% of the vote, Joshua 31.4% of the vote, Dylan with 28% of the vote, and Ellie over here with 0% of the vote. So this is the theoretical versus experimental measures, theoretical being the voted, experimental being the real measures. As you can see, Olivia was both for voted and real, as well as Ellie for voted and real. In last place, though, these two just switched, not really a big deal, just by 1 vote. And I think that just because more girls voted for him instead of him, just by 1, so that wasn't a big deal. So this is the first graph I did. It's pretty basic. It just shows as the symmetric difference increases, the votes decrease. So we have a 0.6 to 14, 0.9 to 11, 1.1 to 10, and 0 to 2. This second graph shows our facial dimensions on the horizontal axis in comparison to the values or measurements of those facial dimensions on the vertical. So you can see the average line is this red line right in the middle. It's just the average of all of their measures. So Olivia, you can see, is closest to the red line the whole entire time, pretty much, except at the end. But she almost stays right on top of it the whole entire time because she is the most symmetric in comparison to the 2 other right here, represented by the blue and yellow line. They are still close to the red line, but not as much as Olivia. And then we have Ellie. She's pretty much like an outlier, not really even close to the other ones, which is why she was least symmetric. Okay, this is my final graph. It shows the facial dimensions versus the symmetric differences. So what we want is a downward trend closest to zero, because the closer to zero it is, the more symmetric the face is. So we can see Olivia, it has a downward trend, which is why she's most symmetric, followed by Dylan, has a tiny spike up to 0.4, and then a decline down to zero, not a downward trend, but still not as high a spike as the other two, which is why he was second symmetric. And then we have followed by Joshua, who was ranked third. He had a steeper incline up to 0.5 and then a steep decline down to 0. And then Ellie, which was fourth symmetric, least symmetric, had a high spike up and then a high spike back down and then a smaller spike down, which is why she was least symmetric. She showed no type of trend line down and only spiked up. So in conclusion, as facial symmetry increases, so does the attraction for that face. Measuring results corresponded to the attraction survey, so the most voted on face was also most symmetric, and the least symmetric was also least voted on, so that proves my original claim. We can say that if the face shows more symmetry, it is more likely to have a high chance of being attractive to other individuals, which proves my claim. Thank you for listening, and are there any questions?